So hopefully you got a chance to do that homework. And the answer is that it is the case that these two vectors are orthogonal to each other. And how do we prove that? Well, somehow we need to come up with this right here. And the way you do that is you say, well, we can always take this equation and we can hit it on the left by vector xi transpose. Actually, we started with this equality right here. And then you can bring the scalar outside and you end up with this right here. And notice that what we've now done is we've isolated this right here. It's also the case that this is equal to this. Why is that? That's a matter of looking at this, recognizing that if you reverse the order and transpose the parts, then you can pull the transpose out. And then you recognize that this right here is just a times xi. Why? Because a is symmetric. And then you recognize that a times xi is just lambda I times xi, where this transpose initially probably should be on the outside here. And that then is just equal to this right here. Okay, but we know that these two are equal. So now we have that this is equal to that, 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 is equal to that. And what does that mean? What it means is that lambda j xi transpose xj is equal to lambda I xi transpose xj. Now, if this is not the case, then we could cancel these two and we would conclude that lambda j is equal to lambda I. But we assumed that those were not equal, so that's a contradiction. And therefore we know that xi transpose xj must be equal to 0. In other words, they must be orthogonal to each other.